Today I wanted to present about underwater and water-air optical wireless communication of underwater. Outline includes background and motivation, underwater OWC, water-air OWC, a brief survey on underwater optical wireless communications, real-time wave mitigation for water-air OWC systems via beam tracking, empirical modeling and analysis of water-to-air optical wireless communication channels. In recent years, underwater activities have been intensified due to various reasons, with the depletion of land-based resources. Exploration for new resources underwater is necessary. Other activities such as military and archaeology. Underwater communication requires high-speed, long-distance, low latency, which is important if you need to navigate the underwater vehicles. The UOWC link can be implemented with wired or wireless. The wired system using electrical or optical cable can provide a higher reliability, high data rate, and the possibility of supplying the power of IUV through cable. Wireless communication systems are more flexible, allowing for multi-user communication and no wire tangling problems, but it has high attenuation and the channel is less stable. UOWC affected by bubbles. Let's look at the air bubbles. Air bubbles can be generated from different origins. In the upper sea level, it is mainly generated by rain, breaking waves, or human activities. At the seabed, air bubbles can come from biological or geological sources. The bubble characteristics that affect the communications include the bubble's density, bubble size, and moving speed. The bubble size itself depends on the water depth. So the deeper it goes, the smaller the bubble size and the bubble density. Bubbles may degrade the communication channel. They can cause a deep fade or light scattering, resulting in communication failure. So how can we resolve this problem? The best answer is that using a wider beam. Some of the light will not be affected by the bubbles. It is shows that various of fadings can be reduced, as shown here using the beam explanation. However, the trade-off is the single level is also reduced, so there is an optimum value for the beam extensions. Recently, using spatial diversity with 2x2 MIMO systems to mitigate bubble impairments is proposed. The effects for bubbles with different sizes and different positions are categorized. P1, P2, P3s, and repetition coding and maximum ratio combinations for use in the experiments. It is shown that when the bubble position is close to transmitters, more packet experience deep fade, resulting in a higher data rate. By using 2x2 MIMOs, significant reduction in packet loss is achieved from 34% to less than 1%. This verified that spatial diversity is effective in resolving a bubble induced impairments. And next, we will discuss the OWC link that goes to the troublesome water-air interface. When IUV moves around in the sea, it would be very desirable if IUV's data or video can be transmitted back to the control centers immediately. In that case, a drone in the air can serve as a relay. Due to the service waves, the water-air optical links can be very changing because of high attenuations caused by the light deflections at the water's surface. The basic function is demonstrated in this slide. Using diffuse line of sight OWC, wider coverage for signal reception can be achieved to overcome the wave-induced effects. Here, two wave level and three different modulations formats were investigated. Under the strong wave using the OFDM, it has achieved a high data rate of 30 megabytes per second and 20 centimeter coverage lines, the photodetectors with 2.5 centimeter offset. It is observed that waves can induce a frequency domain power fading. Recently, the use of precoding scheme, discrete circulant transform spread OFDM to combat this problem is proposed. They categorize the wave height, and the incident angles correlate well with the wave level set by the wave generator. It is shown that power fading increased as the wave level increased as expected. Acoustic, RF, and optical wave systems are the technologies that are used for carry out underwater wireless communications. Figure 1 compares the performance of acoustic RF and UOWC based on the transmission range and the data speed bandwidth. UWC is an excellent technology. It has the advantage that it is much more difficult to intercept than traditional underwater acoustic communications. This figure shows a dynamic positioning debris capable of communicating with satellite and via bi-directional UWC with optical surveillance station positioned on the seabed. This slide shows a typical UWC scenario. This shows several platforms, divers, ships, submarines, sensors, and etc. connected by beams of light. Here you can see the seawater light transmission model, and you can see here the schematic of a typical UWC link. As in the water-air OWC channel, dynamic ocean waves may significantly deflect the light beam from its original direction, thus deteriorating the communication performance. Here in this study, a beam tracking system to mitigate wave-induced communication degradation is experimentally demonstrated. Here, when a light beam propagates through the water-air interface, the light spot position on the receiver varies with the change of the Wave's law, resulting in a time-varying offset from the detector, as shown in the figure 1a. And in part B shows the MEMS mirror correction adjustment to recenter the beam at the CCR and the PD array. And part C shows the enlarged view of the transmitter side of B. The schematic of the beam tracking system based on MEMS mirror is illustrated in figure 2A, and B is experimental setup. The normalized intensity of the received optical signal and the light spot displacement trace with and without the beam tracking are shown in this slide. Another study focuses on the modeling impulse response of a W2A OWC channel under different turbulence water surface conditions. Here, the experimental setup of the optical receiver and transmitter employed in the W2A OWC channel is demonstrated in the figure 1. Figure 2, experimental results for the W2A OWC channels. A to C, from left to right, I diagrams for the 100 kilobyte per second of transmission data rate when the W2A interface has no wave, pulse waves, and random waves respectively. D to F, ultrasonic surface mapping when the W2A interface has no waves, pulse waves, and random waves respectively. G to I, histogram and estimated period for the channel impulse response when the W2A interface has no wave, pulse wave, and random waves respectively. J, comparison between impulse response of the channel in both absent and present of the pulse waves in the water surface. K to I, the normal probability plot of the empirically derived impulse response of the channel along with a normal probability plot of the estimated Bias and log normal distributions in the presence of a pulse and random waves respectively. Here we have the summary. Recent progress in UOWC as well as the mitigation methods for bubble and wave-induced impairment are presented. Further UOWC performance enhancement can be realized by device improvements, advanced DSPS, and multiplexing schemes. For the challenging water-air OWC, the wave issue is critical and demands ingenious solutions for wave mitigation. This may include the tracking system optimization, novel signal processing for wave prediction, mitigation, and more devices. Thank you so much.